It is a deep mystery why there is something rather than nothing. And connected to that, how could nothing turn into something? These are deeply puzzling ideas. It was once said that in the beginning there was nothing, which exploded. We call that explosion the Big Bang. And so there's good evidence that around 13.8 billion years ago, our entire universe came into existence in what we're calling the Big Bang. Space, time, energy, all the forces of nature were created in this colossal explosion. Early on, it was just pure energy, but the universe was expanding, space was expanding, and so that energy got sort of diluted in the ever-growing volume of space, and that brought the overall temperature of the universe to cooler temperatures. As the universe expands, it began to cool down, and it cooled down to such a point that a key transition happened. Some of the energy in the universe transformed into particles of matter. As Einstein recognized in his famous equation E equals mc squared, every bit of mass, a particle with mass, has a certain amount of energy locked up in that mass. So even the tiniest amount of mass can be converted into huge quantities of energy. And likewise, energy can be transformed into matter. So matter and energy are two sides of the same coin. Now early on, some of the particles that were produced were familiar particles that we know as constituents of atoms: protons, neutrons, and electrons. There was lots of light as well in the early universe, but it couldn't travel very far without hitting a loose electron. So free electrons do a good job of absorbing light, so light wouldn't be able to get very far before it was absorbed and re-radiated in some other direction. We can think of the early universe then as this kind of plasma, this super hot soup of particles and light, still extremely hot. But as the universe expanded, the temperature cooled. And pretty soon some of these particles are going to assemble into atoms. Now, why do particles assemble into atoms? Because particles have charges. So the protons and the electrons are charged particles. And the electromagnetic force will attract these particles. And that's the force that holds the atom together. The first atoms produced in the early universe were the simplest: hydrogen and helium. Here we see the hydrogen atom with one proton as its nucleus and one electron orbiting the nucleus, and it's the electromagnetic force that is keeping the electron bound to the nucleus of the atom. Now helium is a little more complex. It's got two protons, and the number of protons determines the identity of the atom. But with two protons, there's a problem here, because protons are positively charged. They would repel each other, and the reason the helium atom doesn't decay or break down is because of the neutrons. Neutrons do not have a charge, but they act like a glue that keeps the protons together. And this is what physicists call the strong nuclear force. So the helium atom has a nucleus with two protons and two neutrons. And it's got two electrons. The number of electrons is equal to the number of protons, making atoms electrically neutral. Now, we've also learned that there was a puzzle in the early 1900s that electrons, being negatively charged, should be radiating light as they orbit the nucleus of an atom, but they don't. And all of these puzzles were resolved in what is called quantum mechanics, although it is still deeply puzzling. But the idea now is that electrons do not radiate light when they are in one particular orbital, but there are other possible energy levels that electrons can occupy. And when electrons are moving between these energy levels, that movement is associated with light. So for example, if light with just the right amount of energy strikes the atom, if it has the energy to bump the electron to a higher orbital, the light will be absorbed by the atom. When the electron jumps back down to the lower energy level, then that same light with the same energy is emitted. Here we see the helium atom. The electrons are in the ground state, or they're in the lowest energy level. But if light carrying a certain amount of energy strikes the atom, it can bump an electron up to a higher orbit. That light will have been absorbed, and then when the electron jumps back down, the energy difference then is transformed into light, with a wavelength that carries the energy that is equal to the energy difference of these two energy levels. We drew this process in a diagram like this, where we have the hydrogen nucleus, a single proton, and here's its electron in its lowest energy level. Now if we heat up the hydrogen gas, we can cause collisions that can bump an electron up to the next energy level. When it jumps back down, it's going to radiate light with energy equal to the energy difference of these two energy levels. If there are collisions with greater energy, the electron might be jumped up to the second orbital up here. When it hops back down to the lowest energy level, there's more energy being released, so the light will be a different color. Higher energy light has a shorter wavelength, and so that'll be green here. If the electron makes it all the way up to the highest energy level here, jumps back down, that's the greatest amount of energy being converted into light with the shortest wavelength, highest energy, in this case the blue light. So atoms can emit certain colors of light because electrons can make certain jumps down from higher energy levels. Of course, the reverse of that process is absorption. A red light will be absorbed by this atom because it has just the right amount of energy to knock the electron up to the first higher energy level here. Green light will be absorbed because it has just the right amount of energy to bump the electron up to this energy level, and blue light will be absorbed. It has just the right amount of energy to bump it up to this orbital up here. Now, as these first atoms were forming, as electrons and protons were getting together to form hydrogen and helium, this made it possible for light now to travel much greater distances without bumping into a free electron. And so we can think of then this as a stage in the universe where the universe became transparent. Light was able to travel much greater distances because the particles, the electrons and protons, were getting together into atoms, allowing light free travel through space. And this picture here sort of illustrates that idea that early on it was a soup of energy and particles and light can't travel very far before getting absorbed by a particle. But as atoms started to assemble, hydrogen and helium, then the universe becomes transparent. Light can travel for long distances because the particles get confined to atoms. They no longer interfere with the path of light. Now in this diagram we see the Big Bang here on the left, and then a sort of an illustration of the expanding universe. Now we're not at the point of galaxies yet, but we'll just use this idea of the sphere of the universe is increasing. So the earliest light then was free to travel across the expanding fabric of space. However, because space is expanding, the light waves will be stretched by a factor related to how long the light has been traveling. So as space expanded, the light that was set off on its journey early in the universe, that light, those waves, would be stretched to longer and longer wavelengths. And in fact, in the 60s then, Penzias and Wilson, using their microwave antenna for other purposes, detected this static. They kept getting this static wherever they pointed their antenna. So in the microwave range, and they didn't know where this microwave radiation was coming from. It seemed to be coming from everywhere they would point the antenna in space. And today it is known as the sort of leftover, the background radiation from the Big Bang. So down here in this diagram we have the Big Bang and the visible light that was produced early in the universe, that was finally set free because atoms started to form and the light then could travel without bumping into anything. That light started out with wavelengths in the visible range, but as the universe expanded, those wavelengths got stretched to the microwave region of the electromagnetic spectrum. And this was the microwave background radiation detected by Penzias and Wilson. It is one of the important pieces of evidence that the Big Bang happened. It's like the glow of the universe, the early universe. This is one of the famous pictures of the universe in the microwave range taken by a satellite. And here we see it here. We can think of it as the infant universe. And so what we're getting here is different amounts of the microwave radiation at different levels, so it's sort of clumpy here, and that would indicate the regions, the bright regions here, would be denser regions in the early universe that would have more matter, and those dense regions will go on to form the superclusters of galaxies and galaxies within those clusters. Whereas the darker regions would be empty space between future galaxies. So to summarize then, this moment when the universe became transparent, as the first atoms assembled, the electrons started to orbit their nuclei, forming hydrogen atoms, for example. This meant that electrons were no longer bouncing around to intercept light, so light was able to travel much greater distances in the early universe. And this light then, as the universe expanded, would be stretched. So if it began as visible light, as the universe expanded, the waves were stretched to longer and longer wavelengths till you get down to microwaves, and this is the radiation currently detected on Earth. So this microwave radiation started its journey early in the universe. And this is the picture then of the infant universe, where we see these splotches that will be future galaxies. It's called the cosmic microwave background radiation. Now we're going to locate that famous picture right here in this new diagram. In this diagram we see the entire history of the universe. Big Bang on the left, we have a period of intense energy and pressure. Atoms could not even form at this point. At some point the universe cools as it's been expanding, atoms start to assemble, and light is released. It is set free. And that's the famous picture inserted here. Now after this picture then, it's called the Dark Ages here because at this time there were no stars. It was just hydrogen and helium. They have not yet condensed to form the first stars. So at this stage in the early universe, light had been set free earlier on, but it will take the emergence of the first stars to generate any new light. And we'll pick that up in the next part.